Hey there, future AI wizards. Welcome back to Learning Hub, where we unravel the secrets of artificial intelligence. In this video, we're diving deep into the world with LSTMs with PyTorch, specifically focusing on autoregressive decoding and training without teacher forcing. Buckle up, it's going to be an enlightening ride. So, what exactly are we going to cover today? Well, here's the roadmap. First of all, we'll start with a brief LSTM refresher, where we'll take a quick recap of what LSTMs are and why they're so powerful for sequence data. Then we move on to autoregressive decoding, where we'll break down what autoregressive decoding is and why it's crucial for generating sequences. Next, setting up the LSTM in PyTorch. We'll build our LSTM model from scratch using PyTorch. Fourth, no teacher forcing training. We'll tackle the challenge of training the LSTM without relying on teacher forcing. Fifth, code walkthrough, where I'll walk you through a complete PyTorch implementation of LSTM. Sixth, potential challenges and solutions, where we'll discuss common pitfalls and debugging advice. Seventh, we'll talk about real-world applications and future trends. And in the last point, I'll give you a conclusion and a summary. So let's get started. LSTMs, or long short-term memory networks, are a special kind of recurrent neural networks designed to handle the vanishing gradient problem that plagues traditional RNNs. This vanishing gradient problem occurs because RNNs at the core struggle to retain information over extended sequences, making it hard for them to learn long-term dependencies within the data. LSTMs solve this using a more complex cell structure with gates. Think of these gates as regulators that control the flow of information into and out of the cell state. These gates are forget gate, input gate, and output gate. Forget gate decides what information to throw away from the cell state. Input gate decides what new information to store in the cell state. And output gate fixes what information from the cell state to the output as hidden state. The cell state is like a conveyor belt carrying information across many time steps. These gates allow LSTMs to selectively remember relevant information and forget irrelevant information, making them excellent for tasks like natural language processing, time series analysis, and music generation. Got it? Great. Let's move on to autoregressive decoding. Imagine you're writing a story, one word at a time. Each word you choose influences the next one. That's the core idea behind autoregressive decoding. In essence, it's a method where the output at one time step is fed back as the input to the next time step. Think of it this way. An LSTM predicts the next item in the sequence based on all the previous items it has seen. Then, that predicted item is fed back into the LSTM to predict the item after that, and so on. The key here is that we're using the model's own prediction to generate the rest of the sequence. This contrasts with other decoding methods where we might have the entire target sequence available, like in translation with teacher forcing. Autoregressive decoding is essential when we want to generate new sequences like text, music, or code. Alright, now we'll get our hands dirty with some code. We'll use PyTorch to create a simple LSTM model. First, we need to import the necessary libraries. Torch is the main PyTorch library. Torch.nn contains model for creating neural networks, and torch.optim provides optimization algorithm. Now, we'll define our LSTM class. The init function is the constructor. Input size is the number of features in the input, and hidden size is the size of the hidden state, meaning how much information the cell remembers. Output size is the size of the output. Batch first equals to true tells the LSTM that the first dimension of the input is the batch size. Forward function defines the forward pass of the LSTM. It takes the input and the previous hidden state, passes them through the LSTM layer, and then passes the output through a linear layer to get the final output. Init hidden initializes the hidden state and cell state to zeros. LSTM need an initial hidden state. Now, we'll define our model parameter and instantiate the model. We'll put input size as 10, hidden size as 128, output size as 10, which is same as input size predicting one of the 10 characters, and LSTM model we basically call the constructor of the previously created class. Okay, this is where things get interesting. Teacher forcing is a common technique where during training, we feed the actual target output as the input to the next time step instead of the model's predicted output. However, when generating sequences in the real world, we don't have the correct target. We only have the model's previous prediction. Training without teacher forcing forces the LSTM to learn to rely on its own prediction, making it more robust during training. Teacher forcing can lead to a mismatch between training and inference. This model becomes overly reliant on having the correct previous input, which it won't have during generation. That can basically result in poor performance. So, training without teacher forcing is a more challenging task as the model has to learn to correct its own mistakes. The error can compound over time if the model predicts incorrectly. So now we'll implement the training loop without teacher forcing. I'll create a dummy dataset first. So in the code above, criterion where we have used nn.cross-entropy loss. So we basically use cross-entropy loss for this classification type problem. We've used Adam optimizer. It is used to optimize the model. The outer loop that we see here iterates over each epoch and the inner loop runs for sequence length. We feed in the predicted output from the previous time step as the input to the current time step. So loss.backward computes the gradient of the loss with respect to the model's parameter. Optimizer.step updates the model's parameters using the computed gradients, and optimizer.zeroGrad resets the gradient to 0 before the next iteration. Training without teacher forcing can be tricky. Here are a few challenges on how to tackle them. First, instability during training. The model might diverge and produce nonsensical outputs. So for the solution, we can use gradient clipping to prevent exploding gradients. Experiment with different learning rates can be done to see whether we get a stable result during training. The second challenge is slow convergence, meaning training can take much longer. So for the solution, what we can do is we can try to implement different optimization algorithms like AdamW. We can also increase the size of, or we can also increase the hidden size of the LSTM. The third challenge is accumulation of errors, where the model might get stuck in a loop of bad predictions. So for the solution, we can carefully tune hyperparameters here. We can also try introducing a small amount of noise to the input to help the model escape the local minima. LSTM has been revolutionary in various fields of AI. Text generation, music generation, speech recognition, or self-driving cars. Future of LSTM involves the combination of LSTM with transformer that makes it faster and have the advantages of parallelization while also retaining the ability to process sequences. And that's it. You've learned about LSTMs, autoregressive decoding, and how to train them without teacher forcing. Remember, this is a more advanced technique, so don't get discouraged if it takes some experimentation to get it working well. Key takeaways. First of all, LSTMs are powerful for sequence data due to their gating mechanisms. Second, autoregressive decoding allows us to generate new sequences using the model's own prediction. And third, training without teacher forcing is more challenging but leads to more robust generation. Finally, thanks for watching. If you found this video helpful, please like, subscribe, and hit the notification bell for more AI adventures. Until next time, keep learning.